Let me begin by just reviewing where we were, which was already last Wednesday. The idea is that we're interested in evolving a coherent state in quantum mechanics in time, partly as a way of understanding what its relationship is to classical mechanics. Coherent state has a minimum values of the product of the dispersions of x and p, and so in some sense it represents a quantum state that is as close as possible to a classical state. So in the present case, we're thinking of a coherent state which is centered, has expectation values, that is to say, we think of it as being centered on a position x0 and p0 in the phase space. You can think of it as being a blob centered around that position. We identify phase space with a complex plane by introducing complex coordinates, x plus it over square root of 2, so the real and imaginary parts of the complex coordinate z are the same things, apart from the square root of 2, they're the same things as the position and momentum of the particle. Anyway, we then define a coherent state we call Z0, which is centered at that position. This is the Heisenberg operator acting on the ground state. And we're going to be interested in the exact quantum mechanical time evolution operator applied to this initial state Z0, just to see what happens. How does it compare to the classical motion? Then, last time, by using some operator relations, we succeeded in expanding this coherent state Z0 as a linear combination of energy eigenstates. This is a preliminary step towards computing the time evolution. As you know, you frequently do this by expanding the initial conditions as a linear combination of energy eigenstates. This is an interesting sum because it gives us an explicit formula for the coefficients. These coefficients, which are C0 to the n over the square root of n factorial, you could, of course, also obtain them just by doing an integral of a Gaussian wave packet, which is this initial coherent state, against the harmonic oscillator eigenfunctions, which have Hermite polynomials and stuff in them. It would be kind of a hard way of doing the finding the coefficients, but by operator methods without too much trouble, we get the coefficients here. There's these z0 at the end over root n factorial. Well, in any case, that's most of the work towards finding the time evolution. The reason is that the u of t is the same thing as, of course, e to the minus I t times the Hamiltonian. Here, remember, we're setting h bar equals to 1, and so all these dimensionless units. And the Hamiltonian acts on its own energy eigenstate and brings out its eigenvalue, which is n plus a half in these dimensionless units that we're using. So it makes it easy to apply u of t to both sides of this equation. On the left-hand side, we get u of t acting on z0, which is what we want. And on the right-hand side, the u of t comes through and acts on the eigenstate n. And so we get the same sum, n equals 0 to infinity, with the same coefficient, z0 to the n over square root of n factorial. But then u of t acting on n just brings out the exponential of e to the it minus it times the energy eigenvalue. So it's e to the minus it times n plus a half acting on, multiplying onto the energy eigenstate n. This is the phase factor. All right. Now, there's two parts to this. There's the n part, and then there's the half part. The n part depends on the summation of the index of summation, and the half part doesn't. So I could take the half part out of the sum. And what's left over is the n part. I've got e to the minus itn multiplying z0 to the n. This gives us a combination, which I'll call z of t, which is defined here to be z0 times e to the minus it. Well, last time I showed that this is just a definition that's convenient for this quantum mechanical calculation. The last time I showed that this is actually also the same thing as the classical evolution in phase space in these complex coordinates. So if I think of this as an initial, this x0, p0, or equivalently z0 as an initial condition, the orbit is a circle. I'll try to draw it without getting it too lopsided. If you think of this here, you have some final time z of t down here, so this is the z0, or equivalent to the z0. Then z of t is equal to e to the minus it times z naught, and the t is the angle. It's just a clockwise rotation in the complex plane. So in other words, the classical solution is coming out of this quantum problem. And we can write the answer like this, that u of z0 is equal to, first I'll write the e to the minus it over 2, which is this constant factor that came out. And then we have the sum n equals 0 to infinity of now z of t raised to the nth power divided by root n factorial multiplying energy eigenstate n. This is the same sum we got earlier in expanding the initial state, except that instead of z0, we've got z of t. And so this summation then is the same thing as a coherent state. I can write it this way as e to the minus I t over 2, a coherent state which is centered at location z of t in phase space. And this is not u, let's say this wrong. This is u of t, I wrote this wrong. It's u of t acting on the initial state z0 is equal to this. So this is the time-evolved state in quantum mechanics. And what you see is that it is proportional to a coherent state. It's a phase factor times a coherent state. That means that the minimum uncertainty condition, which is that delta x equals delta p equals 1 over root 2, that's our definition of a coherent state for the purposes of these last couple of lectures. And what we see is that a coherent state remains a coherent state. These dispersions don't change. So the wave packet neither spreads nor anything else. It just stays the same, delta x and delta p. But its center, or its expectation values, move and exactly follow the classical motion. Well, the fact that the expectation values follow the classical motion is a consequence of the Ehrenfest relations and the fact that the Hamiltonian is quadratic. So we kind of knew that already. But this gives us further information. It tells us that it remains a coherent state, and moreover, there's an overall phase factor, which is this e to the minus I t over 2. Anyway, so this is the main result of this, which is an explicit demonstration of how the wave packet, in this case a coherent state, follows the classical motion and remains a minimum uncertainty wave packet in the course of time. This calculation in different form was first carried out by Schrödinger in his 1926 paper, very first paper on quantum mechanics. He solved this problem. He used Hermite polynomials and so on to do it without operators. All right. So the lesson of this is the relationship between the classical and the quantum problem, which is particularly close for harmonic oscillators. Let me just mention one thing, which is that if we had chosen an initial state in which the dispersions were not equal, like this, but perhaps it was still a minimum uncertainty coherence of wave packet. Let's suppose, for example, delta x were 1/2 and delta p were equal to 1, then the product delta x delta p still has its minimum value, which is 1/2. So this is a minimum uncertainty wave packet, all right, but the delta x is now smaller than it was for the coherent state. This is what's sometimes called a squeeze state. Squeeze states have been of interest lately because you can actually prepare them experimentally in quantum optics. It requires nonlinear optical elements to create them. But in any case here, the squeeze state, you can kind of think of that as something in phase space. You see the delta x has been squished by a factor of 1 over the square root of 2, but the delta p has been stretched by the same factor, so the product remains invariant. You can think of this in phase space instead of this picture I drew here. You can think of this, something that's been squished like that, the ellipse sticks out upwards like that. And if you go through a similar analysis, it's more challenging now for the squeeze state to work out the time evolution. But if you go through it, you'll find that the expectations of delta x and delta p actually breathe in and out. They're periodic, not with the period of the oscillator, but with twice the period of the oscillator. So there is spreading and contracting in the wave packet, one might say, but it returns to a squeeze state with minimum uncertainty after a single cycle. If it weren't too hard to do this, I'd give it as a homework problem. I think it's too much formalism for the value you get out of it, but it's not that bad a calculation to do that and show that this is what happens to the dispersions in the case of the squeeze state. All right. Well, this is essentially all I want to say for now anyway for harmonic oscillators. So let me ask if there's any questions about this general subject before I move on to the next one. And if not, I'm going to start then on our next topic, which is propagators and path integrals. First, so I'll cover coherent states now. So first of all, let me just say a few words about path integrals. The path integral is a formulation of quantum mechanics that in some respects is alternative to the usual one which is based on the Schrödinger equation and Hamiltonians. In fact, the path integral is based on Lagrangians, or classical Lagrangians, as a matter of fact. So it turns out there really is a Lagrangian operator, unlike the Hamiltonian operator. The Lagrangian that appears in the path integral is in a sense, the classical Lagrangian. But the result is that it's a different formulation of quantum mechanics. It wasn't at all, the path integral came after the Schrödinger Hamiltonian formulation of quantum mechanics. It was worked out by Feynman in the late 1940s, and it's particularly valuable for relativistic problems where one requires covariance under Lorentz transformations. The path integral formulation is particularly suitable for that. In any case, all I'm going to give you here today, and probably it'll be Wednesday's lecture also, is just a bare introduction of path integrals, but it contains the main ideas, and it's actually quite an interesting approach to quantum mechanics. By the way, Feynman's development of quantum mechanics was based on some earlier, somewhat incomplete ideas by Dirac, which he then put together, and he made a very good use of this in the early days of quantum electrodynamics. In those days, one of the problems was to find covariant formulations of quantum mechanics, and Feynman did this in his own work, primarily through the use of the path integral. All right. In any case, the path integral concerns the propagator. And what is the propagator? The propagator is basically the matrix elements of the time evolution operator. Let's be specific. In this presentation, I'm going to make it simple and talk about just a one-dimensional problem where the Hamiltonian is a kinetic plus potential Hamiltonian. So let's write it as T plus P for kinetic plus potential energy. And then the time evolution operator then, assuming the potential energy is independent of time evolution operator is e to the minus IT h over h bar. I'll go back to ordinary units now. The propagator is basically the x-space matrix elements of the time evolution operator, like this. I'll put this in quotes and call this the propagator. One reason I put it in quotes is that this isn't exactly, there's very slight changes in this is what you will find in the literature as the definition of the propagator, but I'm trying to make the discussion simple, so for us, this will do. Later on in the course when we talk about Green's functions, I'll be more detailed about it. In any case, this is all we need to know. It's basically the x-space matrix elements of the time evolution operator. Now this means that this quantity, the propagator, you can also give it a name. Let's call it capital K. It's a function of two positions x, x0 in elapsed time t. We think of the x0 as being in some sense an initial position. The reason why we call it that will be apparent later on. And we think of this x over here as a final position. You can also think of an initial and final time. Here the t equals 0 is initial time, and this t parameter here is the final time. Of course, the ket x0 stands for a singular quantum state in which the particle is concentrated in an infinitesimal region around the point x0. We can't really realize such a state in practice because it's not normalizable, but it's an idealization or a limit of realistic states. And then if we apply u of t to that, it's like saying, well, we knew the particle was at position x0 at the initial time. We then evolve in time. Then when we take the scalar product of x, we're finding the amplitude to find the particle at a particular final position at a later time. Squaring this, in a sense, gives us a probability or a probability density for finding the particle at some variable final position, if you think of this as variable and x0 as being fixed. This is a way of visualizing this and also attaching language to it, an amplitude to find the particle at a final position, given that it was at some initial position at some initial time. All right. Now, the propagator can be used to advance wave functions in time. Because if I have, as you know, the time evolution operator maps states in ket language. It looks like this. If this is the initial state, and u of t maps it into the final state psi of t. If we define a time-dependent wave function, the psi of x and t is equal to x scalar product with psi of t, then this time evolution equation in ket language becomes this in wave function language. The psi of x and t is equal to the integral of the initial position dx0 of the matrix element x u of t x0 times psi of x0 comma 0. This is just comes from inserting resolutions of the, multiplying this by x on both sides, inserting a resolution of the identity between u of t, letting x0 be the variable of integration, and you obtain this equation. Evolving wave functions forward in time, from the initial wave function to the final one. And this part of the integrand is called the kernel, the integral transform, and that kernel is, by this definition, is the propagator. It's the same as this function, k of x, x0, and t. The propagator is that kernel. I should also mention a pictorial way of thinking about this. This is related to Huygens' principle, which goes back in optics several centuries. The final wave function at the final time is a superposition. That's what this integral is a superposition. It can be thought of as a superposition of, if here's some region where the initial wave function psi of x0 at time 0 is non-zero, is you can think of it as each point of this region where the initial wave function is non-zero radiates a wave. Think of it as being kind of a circular wave coming out, because oftentimes it is. It radiates a wave, and what is that wave? The wave is the propagator. It's a propagator that radiated from position x0, evaluated in the final position in time x and t. And what this integral is saying is the final wave function is a linear superposition of all these waves coming out like this. So this is a pictorial way of thinking of this related to Huygens' principle. Notice that these waves which are radiated out are weighted by the value of the initial wave function at the given point, which is the source of the radiated waves. Okay, now, so that's a little bit of background on the propagator and its X-space matrix elements. One thing I'd like to do right away is to work out an example of the propagator. I'd like to do it for the case of the free particle, just to post it as a result to have. We'll refer back to it quite a few times later on in the course, so let's do it now and just get it. It's just a calculation to find it. So for the case of the free particle, of course, the Hamiltonian is p squared over 2m. I'll put a hat on the p just to emphasize that it's an operator. And so the propagator, k of x, x0 at time t, is equal to the matrix elements between x and x0 of the time evolution operator, which is e to the minus it times p hat squared over 2m, and I also have to divide by h bar. It's equal to that. It's a position space matrix element of basically e to the it squared. Now, we'll evaluate this by inserting a resolution of the identity here somewhere. Here's good enough. So I'll have a pp resolution of the identity with an integral on it. And the result is that this can be written now as an integral pp, and we have a matrix element x, e to the minus I over h bar, p hat squared over 2m, t times t. And then we have pp, and then we've got x0, like this, by inserting resolution of the identity. We do this, of course, because now this operator, the time evolution operator, is a function only of the momentum operator. It's acting on an eigenstate of momentum, so it just replaces the operator by its eigenvalue, which becomes a number, as Direct says, a C number, which we can take out of the matrix element. And so what we get is integral pp of e to the minus it over h bar, p squared over 2m. And then you're left with a matrix element, just xp, error product, multiplying p x0. And these are standard position momentum matrix elements, and the product of those two is equal to e to the I momentum p times x minus x0 over h bar, divided by 2 pi h bar if you multiply those two matrix elements together. Yes?
I'm sorry, I think I just spaced out this here. What happened to the dx0?
There is no dx0. The x0 is just the x0, x and x0 are, think of these as fixed initial and final times. These are the two sides of the matrix element which constitutes the propagator. But if you're going to use it, but if you're going to use it to enhance a wave function, you will need to integrate over x0. So right now I'm just calculating the k. Okay, so this is a Gaussian integral. You see, it's an integral of the momentum. There's a p squared in the exponent and a linear term p in the exponent. And I'll skip the details of doing the Gaussian integral because it's straightforward. And I'll just quote the answer. It is this. Write it out in full. This is k of x, x0, and t is equal to, there's the square root of the mass divided by 2 pi I h bar t times e to the I over 2, we'll write it as I over h bar, and then the mass m times x minus x0 squared over 2t. And let me box that because that's the main result for the propagator of the free particle. There aren't very many systems for which one can calculate explicitly the propagator, but the free particle is one of them, and it appears quite often in practice. And so this is a result that you come back to a number of times in the course. Now, before I leave this, to move on to the path angle, let me just mention one thing, which is that this quantity that appears in the exponent here, which is multiplied by I over h bar, is a quantity that has an interesting interpretation in classical mechanics. It's called Hamilton's principal function. And I'll say more about that later on, but it is a function which plays an important role in classical mechanics. And it's interesting that it's appearing here in this quantum problem of propagating wave functions.
Mr. Woodruff?
Is that your question? Yes.
Was that a 2t in the denominator on the...
Yes, the 2t up there, yes. All right. Now, let me turn to a more general case in which the Hamiltonian also has a potential energy. And in that case, we can't generally write down an explicit formula for the propagator, but there is a version of a general formula for the propagator, which is the path integral, is the main object I want to get to here today. And so let's let h now be px squared over 2m for the kinetic energy plus v of x hat. I'll put hats again to emphasize these are operators. Kinetic plus potential Hamiltonian. Now, we're going to be interested in the matrix elements ultimately, but let's just talk about the time evolution operator right now. This is a simple exponential. It's e to the minus I t h hat over h bar. What we're going to do is to take the time interval t, and we'll write it as capital N times epsilon, where we want to think that the psychology here is one thing of n going to infinity. In other words, we will take n goes to infinity later on, but right now let's make it a large number, as large as you like. And this means that epsilon is equal to t divided by n, and we'll think of t itself, which is the final time here, as just being fixed. So this is the context of these definitions. And the idea is that we're going to split this time interval, finite time interval t, into a large number of small intervals of duration epsilon. So epsilon is like a small delta t here. Then it follows that u of t then is equal to the same thing as u of epsilon raised to the nth power. And therefore, the matrix element, therefore the propagator, which is k of x comma x0 comma t, which is the matrix element of u of t sandwiched between x and x0, can be written this way as x u of epsilon times u of epsilon dot 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 times u of epsilon x0, where there are n factors, total n factors here. So in other words, we're switching over in effect to a large number of small time propagations. And the question is, can we now approximate the small time propagation in some useful way? The answer is yes. It works like this. Let's take the propagator between 2 points x, and I'll call it x prime now instead of x0, of the small time propagation u of epsilon. Let's look at this. This is the same thing as x, of course, e to the minus I over h bar epsilon times the kinetic energy plus the potential energy x prime. That's the matrix element. As far as the operator that appears under the matrix element is concerned, since epsilon is now small, let's expand it in a Taylor series and write it this way as 1 minus I epsilon over h bar times t plus b. And then I'll just write order epsilon squared for the quadratic term. But it's an exponential series, so the terms are easy to write out. This can also be written this way as 1 minus I epsilon over h bar times the kinetic energy plus higher order terms times 1 minus I epsilon over h bar times the potential energy plus higher order terms. Now, if I were to stop there, and you just multiply these two series out to first order and epsilon, it reproduces the line above. So these two series actually agree to order epsilon. I'm intending these series to be both these series in the second line to be exponential series, and if you carry it out to the second order, you'll find it does not agree with the epsilon squared term above. And the reason for that is that if you have operators e to the a and e to the b, this in general is not equal to e to the a plus b. We saw an example of this already in Glauber's theorem, where there were some cases where you could correct for it. In other words, operators don't obey the rules of ordinary numbers when they don't commute. And in this case, kinetic and potential energy certainly don't commute because one depends on momentum and the other on position. However, in the small epsilon expansion, the two do agree. These two exponential series do agree through first order. So if I put an order epsilon squared correction here, this is actually a correct statement. And so I can rewrite this now as e to the minus I epsilon, turning this into a collective series, power series, e to the minus I epsilon over h bar times the kinetic energy times e to the minus I epsilon over h bar times the potential energy plus order epsilon squared, like this. It's a factorization of the approximate factorization for small times of the kinetic and potential energies into these two terms. And so the result is this matrix element now looks like this. It's x e to the minus I, and I'll write the kinetic minus I over h bar epsilon, kinetic energy px squared over 2m. And then minus I to the e to the minus I epsilon over h bar times the potential energy v of x hat, and then multiplying ket x prime on the right hand side. All right, plus order epsilon squared. The error estimate here. Now, for this matrix element that I've got here, allow me to introduce once again a momentum resolution of the identity between these two factors, very similar to what was done in the case of the free particle on the board right above. And this then turns into an integral dp x, matrix element x on the left, e to the minus I epsilon over h bar, px squared over 2m times bra p. In the second matrix elements, ket p on the left, e to the minus I epsilon over h bar v of x hat, multiplying ket x prime on the right, plus order epsilon squared. And now these matrix elements are easy to do because the momentum, the kinetic energy operator is next to a momentum eigenket, and the potential energy operator is next to a position eigenket. So you just replace these operators by the eigenvalues, x prime here and p there. Those just become numbers. So this becomes integral dp, and we get e to the minus I epsilon over h bar, p squared over 2m. Now with no hat on it, this is the p is the same as that momentum value. It's now the variable of integration. And then we've got the remaining matrix element xp. And for this one, we get e to the minus I epsilon over h bar v of x prime, where x has been replaced by x prime. And then we've got the matrix element px prime. If you take these two remaining xp matrix elements together, they're the same thing as e to the I p times x minus x prime over h bar, and the whole thing is divided by 2 pi h bar. Now, I'll clean this up and make it a single integral so it's a little easier to read. So the whole thing here, bring it around, this whole thing becomes over here equal to an integral dp over 2 pi h bar e to the I minus I epsilon over h bar p squared over 2m. plus I over h bar times momentum p times x minus x prime minus I epsilon over h bar v of x prime. Now the momentum integral, which is to be done here, is exactly the same as we had in the case of the free particle on the board above. It's a Gaussian integral. The only thing that's different is that there's another phase here which wasn't there before that depends on the potential evaluated at x prime. The variable of integration is p, so this is just a constant as far as the integral is concerned. And the result is that we get an answer which is essentially the free particle propagator up above, except the t will be replaced by the small time epsilon, and we'll have this phase factor for the potential energy, and there's this plus order epsilon squared correction. So let me just say dot 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 here because I'll fill it in on another board. And what we get is this. Is we get the short time propagator x and x prime sandwiched by u of epsilon is equal to this. It's the square root of the mass divided by 2 pi I h bar epsilon times e to the I over h bar times x minus x prime squared. Mass is in here. Mass times x minus x prime squared twice epsilon. And then what we get is minus I over h bar epsilon times d of x prime. And then we get plus order epsilon squared. That's the short time expression for the propagator approximation. Now, to go back to the actual object we really want, this is the propagator for some finite time, u of t, which is not necessarily small, sandwiched between x and x0. But u of t is u of epsilon raised to the nth power, so this is the same thing as x, and then a series of factors of u of epsilon. X0 like this, and in fact you can see that there are capital N factors here. And so what we will do now is to insert a resolution of the identity between each of these factors. This will now be in position space, in x space, resolution of the identity. Since there's n factors, there's n minus 1 slots between the factors. And we'll call the variable of integration for the one on the right x1, the next one x2, and so on. And this will take us down to x of n minus 1 for the last one, xn minus 2. Series of resolutions of the identity. And just to make the notation more symmetrical, let's take this final position x, and let's just define x of capital N by definition as the same thing as our final position x. And if we do this, then this becomes a product of fact, becomes this. There's an integral over the intermediate x's, dx1 out of dx2 minus 1. And then we've got xn, u of epsilon, xn minus 1, first matrix element. Second one is xn minus 1, sandwiched around u of epsilon, xn minus 2, dot, 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 all the way down to x1, u of epsilon, x0. Like this. It becomes a product of n short-time matrix elements, in short-time propagators. Up to this stage, it's exact. And now, we get to use our short-time propagator, which is up here at the top of the board. Let me box it, because it's the main result of the calculation of the board above. Here's the short-time propagator. Now let's take this short-time propagator and plug it in for each of these factors. So let's take a typical factor here, and let's write a typical factor as x. Let's call it xj plus 1, u of epsilon xj, where j is the index that ranges between 0 and n minus 1. So we need to take this xx prime variables in this short time propagation and replace them by xj and xj plus 1. So if we do this, then you can see that there's going to be these prefactors here with the square root will get raised to the nth power because there's n of them. And this becomes equal to the mass m divided by 2 pi I h bar epsilon to the n over 2 power. And then we've got the integral dx1 dxn, dx1 dxn minus 1, excuse me. And then what we've got is the product of exponentials that are of this form. And the product of exponentials, of course, would be the exponential of the sum. As far as this exponential goes, it's perhaps easier if I factor out the I over h bar. Allow me to do that. I'll put square brackets around this, and I'll take away the I over h bar there. Pardon me for using my fingers on this, but this is all contained in the notes. So then what I need to do is to sum this exponent over terms in which I've got j, xj, and xj plus 1, and where the j runs from 0 up to n minus 1. So what's left in this integral then is the exponential, I'll write it this way, is exponential of, big curly bracket, I over h bar. And then we have the sum from j equals 0 up to n minus 1. And then the first term is the mass m times xj plus 1 minus xj, quantity squared, divided by 2 epsilon, minus epsilon times b evaluated at xj. And that's the sum, and that's the whole thing that appears in the exponent. Okay? Now, there's one problem, which is that I still have to take into account the order epsilon squared. This was only an approximation. I'm putting this approximation into each of these factors, of which there's n of them. And so, because each term has an error of order epsilon squared, when I put this into the factors, you can roughly see that the error is going to get multiplied by a factor of capital N. But remember, n up here is something we're going to take to infinity, so epsilon is like order 1 over n. The t itself is fixed. So n times epsilon squared is the same thing as order epsilon. And the result is although the error gets bigger, it's still only order epsilon. So for some finite subdivision of this time interval, and within segments, we get an error of order epsilon like this. The way to get rid of this order epsilon term is to take a limit in which capital N goes to infinity, in which we divide the time interval up into an infinite number of infinitely small steps. If we do this, then the number of resolutions of the identity of x that are inserted also goes to infinity, and so it becomes an integral over an infinite dimensional space of x's. In any case, let me write out the result by doing that. So we can write it this way. We can say that the propagator is x0 sandwiched around u of t is equal to the limit as n goes to infinity. And then we've got this factor, m divided by 2 pi I epsilon h bar to the capital N over 2 power, an integral dx1 up to dxn minus 1. I've got room to write this down. And then we have the exponential of I over h bar. And let me just let me just modify this expression slightly by factoring out a factor of epsilon. Take a factor of epsilon out, that'll remove it there and make that one into the denominator epsilon squared. So it becomes epsilon times the sum, j equals 0, up to n minus 1, of m over 2, xj plus 1, minus xj, divided by epsilon, quantity squared, minus b of xj, like this. Square brackets are what's being summed, and a closed curly bracket like that. And allow me to box this, because this is regarded as this can be regarded as the discretized version of the path integral in configuration space. I'll tell you in just a moment about why it's considered a path integral, but that's what this is considered to be. In some sense, this is a first major step in the result. It's expressing the propagator in terms of an infinite dimensional integral. Now, I think the first thing to do is to visualize. Well, maybe before I do, let me just make one remark. This stuff I'm doing here with order epsilon squared and order epsilon is it would make a mathematician pull their hair out because it's so unrigorous what I'm doing. I think the best you can say is this is an outline of a suggestion that something like this, that some expression like this should be a representation of the propagator. In fact, it isn't at all easy to make the propagator rigorous. People worked on it for a number of years. To make the path integral rigorous, to understand this limit. Especially when you have an imaginary exponent such as appears here. The imaginary exponent is characteristic of the Feynman path integral. There are similar types of integrals, infinite dimensional integrals, that occur in statistics or statistical mechanics, in which the exponent is real. It's a Gaussian damp, it's a minus sign, it's a Gaussian damping kind of a thing. And those are much easier to make rigorous. In fact, they have a history that goes back before the Feynman integral. It's called the Wiener integral, which we'll say. Actually, I'll say something more about that later on when we talk about the partition function in statistical mechanics. But anyway, for now, we won't worry about any of that. We'll just take this as a formal expression. I can say that this limit this is certainly a limit that can be calculated. And in physical problems, a limit exists, and it does give you the propagator. All right. Now, the next thing to do, I think, is to try to visualize what's going on with this exponent and the nature of this integration. So for that purpose, allow me to make a space-time diagram, trying to draw it big, in which we've got time going off to the right, and we've got space going up vertically. This is just one-dimensional now. We have two positions. There's an x0 and an x. That's our final position. These are just parameters of the matrix element up here, so those are just fixed. But let me extend these as horizontal lines going across here in the space-time diagram. We also have two times. One is t equals 0, which is beginning time, so let me draw a vertical line here coming up. And the other one is the final time t, which we can also call t sub n if you want. In fact, let me define it. Let's let t sub j be equal to j times epsilon, so that t0 is the beginning time and tn is the last time. Then there are intermediate times, t1, t2, t3, and so on, that are just multiples of epsilon, t sub n minus 1, t sub n minus 2 coming back down from the upper time, and then intermediate times in between. Now, for each of these times, let me draw in a dotted line here, like this, a vertical line, which is running parallel to the x-axis, like this. So here's this tn. I'll draw it as a solid line, because that's the fixed final time. Like this. All right. Now, this is an integral, and all of these x's, x1 through xn minus 1, notice these are the intermediate x's. The initial and final x's are fixed. This x is the same thing as xn. Those are fixed, but the intermediate x's are the variables of integration that came from an insertion of the resolution of identity. So let's just take some particular values of x1 through xn minus 1 in order to evaluate the integrand at some point in this range of integration. So let's say maybe x1 is right there, and let's say x2 is there, and x3 is there. And xn minus 1 is here, and xn minus 2 is up there maybe. It doesn't have to be inside the interval x0 to xn. It can be outside if it needs to be. These x integrals go from, I didn't say so, but they go from minus infinity to plus infinity because they came from the resolution of the identity. Okay. So now let's do this. Let's take this point here, which is the point x0 at time t equals 0. We'll regard this as an initial point. And take this point here, which is xn, which is x, at the final time t, which is tn, and regard that as a fixed final point. The initial and final points and times are both of them fixed, and just parameters of the problem. But the intermediate x's are variables of integration. And as I say, let's take specific values of the intermediate variables, and now let's connect them together by solid lines on these intervals like this. And if you do, you get something that looks like this. And for specific values of intermediate x's, you get a jagged line like this, and these connect together in between. They're going to go up and down, and that's what they're going to do something like that. So in a particular set of intermediate x values, what we have here is a discretized version of a path in configuration space that starts at the given initial x point at the given initial time, and ends at the given final x point at the given final time. But in between, the path is allowed to do anything it wants because these x variables in between are variables of integration that go from minus infinity to plus infinity. And so for a fixed value of capital N, what we have is we're really integrating over all discretized paths that have fixed initial endpoints in times. And in conception, at least, when we let n go to infinity, we're integrating over all possible paths connecting those 2 points in space. And so in some sense, the variable of integration here, it's being represented as a bunch of intermediate x's, but in some sense, the variable of integration is a path in configuration space with fixed initial and final positions and times, but in between allowed to do anything. And so this leads to some change in notation in this path integral. It's more abbreviated notation, and you see this is rather lengthy to write this out. One thing we can say is let's replace this dx to dxn minus 1. Let's just write it as d of x of tau, like this. I'm using tau now for a variable intermediate time. I don't want to call it t because t was our fixed final time. So tau just is something that goes between t equals 0 and t. The tau equals tau equals t. But anyway, the idea of this is this represents, in effect, a volume element in path space. As for the exponent up here, what about that? What we've got here is a sum, as you can see easily. It's a sum. And let's do this. Let's change notation a little bit. Instead of epsilon, let's write delta t. That's kind of what it is because it's a small time increment moving down this time interval has been split up. And let's take xj plus 1 minus x of j. Let's call this delta xj, like that. Now I'm running out of room. Because if we do this, then the exponent takes on an interesting form. It turns into the integral of the classical Lagrangian. Because that sum, which is up there in the upper right corner of the board, it turns into this with this change of notation. It turns into j from 0 to n minus 1 of delta t. It's the mass divided by 2, delta xj divided by delta t quantity squared, minus the potential v evaluated at xj. So lying behind this is a limit in which the n is going to infinity. This sum is what you'd call a Riemann approximation to a Riemann integral, which would look like this. Integral from 0 to t d tau. D tau is replacing the delta t here, times m over 2 x dot of tau quantity squared minus v of x of tau. And this is the same thing as integral from 0 to t d tau of the classical Lagrangian evaluated at x of tau and x dot of tau. Lagrangian is a function of the x's and x dots of the system, and for a kinetic plus potential Hamiltonian, Lagrangian is kinetic minus the potential with a change in sign. And that's what you're seeing here, is 1/2 mv squared for the kinetic energy and then minus potential energy. So this appears to be a Riemann, as I say, it appears to be a Riemann sum approximation of this integral, which is the integral over time of the Lagrangian. And as we say, this is the integral of the Lagrangian along a path, x of tau in configuration space. And because of these fairly simple associations, there's a more compact way of writing a path integral. It looks like this. It says that you write x u of t x0, that's our propagator, is equal to the normalization constant that I'll just call capital C. That's really the same thing as that m over 2 pi I epsilon h bar to the n over 2 factor, all that stuff. Let's just call it C. And then we say integral, and then instead of the dx1 to dxn minus 1, let's write it as d of x of tau, which means the volume element in path space. And then for the exponent, we get e to the I over h bar, the integral from 0 to t of the Lagrangian evaluated on the path x of tau and x dot of tau d tau. And this is just notation, but it's a more compact notation than the one up above. And it's actually, this is actually quite an interesting one to play around with. You can play some interesting games with this expression. Now, however, it's just notation, and there's some things you need to be aware of. Let's go back to this picture of the discretized path. I drew it kind of jagged, as you see. Recall the idea was that we were just going to pick some variable, some intermediate variables of integration, x1 through xn minus 1, put down dots, and then connect them with straight lines. However, each of those intermediate variables of integration, let me bring the board down so I can point at it better. Each of those variables of intermediate variables of integration actually ranges from minus infinity to plus infinity. So let's suppose we hold all of these x's fixed except for one of them, like maybe x3 here. The x3 is underneath this t3 variable. So all this jagged curves looks just as I drew it, except for this one. This point is going to be allowed to go from minus infinity all the way to plus infinity, which is necessary in doing the integral. Well, what you see is that you get a path in which the delta x, which is the jump from x2 to x3, ranges all the way from minus infinity to plus infinity. And it does so in a delta t, which is this epsilon, which is going to 0. And as epsilon goes to 0, this delta x does not go to 0. It's going to go all the way between minus infinity to plus infinity in these intervals. So what it looks like is that these paths that we get, the typical path that occurs in the path space, is one for which, as delta t goes to 0, the delta x goes to infinity. That's what it seems like. For most of the paths anyway, that's what it looks like. Well, if this were true, then you'd have a path that you would say is not continuous. Because a continuous path is one for which the delta x would go to 0 as delta t goes to 0. Well, that's bad because it means these paths are really crazy. They aren't like ordinary smooth paths in configuration space. As it turns out, this is actually not quite the correct conclusion. It is true the variable delta x goes to infinity in the integral, but as it turns out, the major contributions to the integral occur only over a limited range of delta x, and instead this should be replaced by delta x is of the order of the square root of delta t. Not because as I say, not because the range of integration is limited, but just because this is, as it turns out, and I'll show you this next lecture, the dominant contributions to the integral come only over this more limited range of delta x. And thus, for the paths that we have here, we do find that as delta t goes to 0, we take the limit n goes to infinity, the delta x also goes to 0. And thus, the typical paths that really make a contribution to the path integral actually are continuous. However, it's still kind of strange because if we compute the velocity, which is delta x over delta t, and we take the limit where n goes to infinity, since delta x is limited to a range of the square root of delta t, this goes as 1 over the square root of delta t, and thus this goes to infinity as 1 goes to infinity. And so what we have is a set of paths, typical paths which contribute to the path integral, are paths which are continuous, but they are not differentiable. They in fact have infinite velocity everywhere. They jump up and down with infinite velocity, but they do so in such a way that they are in fact continuous. One of the ways of visualizing this is to think of a Brownian motion, in which a Brownian motion is a random walk in which the particle makes very small steps, and over a large period of time it randomly walks through space. I hope you know that for a random walk, that delta x goes as the square root of delta t. In fact, it's the same scaling laws as I'm speaking of here. And so, one of the ways of visualizing these paths is in order like the paths of a Brownian particle undergoing random motion. Maybe another way of visualizing it is to say that it's like white noise in an oscilloscope trace. White noise has all frequency components out to infinity. It means that in a sense, white noise is a curve which is continuous but not differentiable. So those are the typical paths that go into this. Well, I probably better stop. Carry this forward next. Let me begin by just reviewing where we were, which was already last Wednesday. The idea is that we're interested in evolving a coherent state in quantum mechanics in time, partly as a way of understanding what its relationship is to classical mechanics. Coherent state has a minimum values of the product of the dispersions of x and p. And so in some sense it represents a quantum state that is as close as possible to a classical state. So in the present case, we're thinking of a coherent state which is centered, has expectation values, that is to say, we think of it as being centered on a position x0 and p0 in phase space. You can think of it as being a blob centered around that position. We identify phase space with a complex plane by introducing complex coordinates, x plus it over square root of 2, so the real and imaginary parts of the complex coordinate z are the same things, apart from the square root of 2, they're the same things as the position and momentum of the particle. Anyway, we then define a coherent. I'll try to draw it without being too lopsided. If you think of this here, you have some final time z of t down here, so this is the z0, or equivalent to the z0. Then z of t is equal to e to the minus it times z naught, and the t is the angle. It's just a clockwise rotation in the complex plane. So in other words, the classical solution is coming out of this quantum problem. And we can write the answer like this, that u of z0 is equal to, first I'll write the e to the minus it over 2, which is this constant factor that came out. And then we have the sum n equals 0 to infinity of now z of t raised to the nth power divided by root n factorial multiplying energy eigenstate n. This is the same sum we got earlier in expanding the initial state, except that instead of z0, we've got z of t. And so this summation then is the same thing as a coherent state. I can write it this way: as e to the minus it, e to the minus it times n plus a half, acting on multiplying onto the energy eigenstate n. It's just a phase factor. All right. Now, there's two parts to this. There's the n part, and then there's the half part. The n part depends on the summation of the index of summation, and the half part doesn't. So I could take the half part out of the sum. And what's left over is the n part. I've got e to the minus itn multiplying z0 to the n. This gives us a combination, which I'll call z of t, which is defined here to be z0 times e to the minus it. Well, last time I showed that this is just a definition that's convenient for this quantum mechanical calculation. The last time I showed that this is actually also the same thing as the classical evolution in phase space in these complex coordinates. So if I think of this as an initial, this x0, p0, or equivalently z0 as an initial condition, the orbit is a circle, and state we call z0, which is centered at that position. This is the Heisenberg operator acting on the ground state. And we're going to be interested in the exact quantum mechanical time evolution operator applied to this initial state z0, just to see what happens. How does it compare to the classical motions? But then, last time, by using some operator relations, we succeeded in expanding this coherent state z0 as a linear combination of energy eigenstates. This is a preliminary step towards computing the time evolution. As you know, you frequently do this by expanding the initial conditions as a linear combination of energy eigenstates. This is an interesting sum because it gives us an explicit formula for the coefficients. These coefficients, which are z0 to the n over the square root of n factorial, you could, of course, also obtain them just by doing an integral of a Gaussian wave packet, which is this initial coherent state, against the harmonic oscillator eigenfunctions, which have Hermite polynomials and stuff in them. It would be kind of a hard way of doing the finding the coefficients, but by operator methods without too much trouble, we get the coefficients here. There's these z0 at the end over root n factorial. Well, in any case, that's most of the work towards finding the time evolution. The reason is that the u of t is the same thing as, of course, e to the minus it times the Hamiltonian. Here, remember, we're setting h bar equals to 1, so all these dimensionless units. And the Hamiltonian acts on its own energy eigenstate and brings out its eigenvalue, which is n plus a half in these dimensionless units that we're using. So it makes it easy to apply u of t to both sides of this equation. On the left-hand side, we get u of t acting like z0, which is what we want. And on the right-hand side, the u of t comes through and acts on the eigenstate n. And so we get the same sum, n equals 0 to infinity, with the same coefficient, z0 to the n over square root of n factorial. But then U of t acting on n just brings out the exponential of e to the it minus it times the energy eigenvalue. So